Okay, YouTube, in this video, I'm going to work with you on the process of long division with polynomial expressions, but also kind of relate that to what we refer to as the division algorithm, okay? And so what we're essentially trying to do is we're going to be given two different polynomials. I'm going to refer to this one right here as our f of x, our original polynomial, and we're going to divide it by this thing right here. I'm going to call this d of x, or in other words, our divisor. So before we do this and relate it to the division algorithm, let's go ahead and recap what we mean by long division in the first place. If I were to have, say, an expression like 128 divided by 2 here, we would refer to this first expression right here as the dividend, or the thing that is being divided. So as far as what we're looking at over here, since we're dividing this polynomial by this, we would say that this thing right here really is our dividend, the thing that we're dividing, okay? And the thing we're dividing by, you might recall, is referred to as the divisor, the divisor. So we have this d of x, and I'm going to refer to that as the polynomial that is our divisor polynomial. So this is our divisor, or the polynomial that is doing the dividing. So to do this long division style, essentially what we do is we always put the dividend on the inside of this array here, and we put the divisor on the outside. So things to point out, we have our dividend is what is inside here, and our divisor is what is outside here. What we're going to do is we're going to put up here the answer, and the answer to a division problem is what we refer to as the quotient, okay? And that sometimes we get a remainder, okay? So a remainder could be 0 or it could be non-zero, but sometimes we do get a remainder that we put off on the side. But these are all the parts of this division problem that we're looking at. So the way this works is essentially what we're going to do is we're going to work left to right here with this dividend, and we say, well, how many times would 2 go into 1? Now, when I say how many times does 2 go into 1, really what I'm asking is, what can I take times 2 to get it to come out to be exactly 1? And there are no values for which I can do this. So we're going to divide. The next step is going to be to multiply. So we'll take our 0 times 2 here. We get 0, and then the next step naturally is to subtract this. We get 1 minus 0, we get 1. We would carry down the 2, and then we would just begin again, where this time I'm saying, well, how many times does 2 go into 12? Again, I want to ask this question. If I ask, how many times does 2 go into 12, what I'm really asking is, what can I take times 2 to get 12 exactly, or as close as I can to it? In this instance here, I would say, well, 6. So we'll go ahead, we did our division, we'll multiply, 6 times 2 is 12, and we'll subtract all of this 12 right here from this 12, and I get 0, then we'll carry down, and we'll begin again. Except this time I'm saying how many times does this leading thing go into this thing right here? We would say 4. So we get 4 times 2 is 8. We're going to subtract all of this 8, and I get 0. So I know that I'm done when I've reached the end of this right here. I don't need to add on any decimal value and continue. When it comes to polynomial division, we'll treat it the same way. But we would say that this thing right here, it's important to note that this is our remainder, okay? So going backwards, we would say, well, what is the significance of this divisor here 2 and its relation to this quotient 64? What we could say is that the initial value that we started with here, our 128, we could really rewrite this as the divisor, which in this case was 2, times the quotient that we got. So 2 times 64, our divisor times the quotient, and then we could say plus the remainder, which in this case is 0. And I want to point this out, since we were dividing by 2, we say 0 over the thing we were dividing by. So as far as we are concerned with, as far as the division algorithm is concerned, it says, well, what if we had two polynomial expressions, f of x, which is our dividend, and d of x, which is the divisor polynomial. And we say d of x isn't equal to 0. We don't want to divide by 0. We would say that also, in this instance, we're going to assume that the degree of the denominator is less than the degree of the numerator. In other words, let's say 128 divided by 2. 2 wasn't greater in value than this 128 right here. Then we could say there exists a unique polynomial set q of x and r of x such that this is true. So essentially our original dividend here, which over here is going to be this giant polynomial, what we could do is we could rewrite it as the thing we divided by times the answer that we got, plus the remainder is what we have left over. So we have the divisor, quotient, this is our answer here, and then the remainder, okay? Essentially, what this allows us to do, this division process here, allows us to rewrite some polynomial as the thing we divided by times the answer that we got plus the remainder, which really what we're doing a lot of the time is trying to factor very large polynomials. And so we try to find things that go into them evenly. So if we say that this d of x, the thing I'm dividing by here, is a factor of f of x, what we know about this is this. We would have no remainder if d of x is a factor. Keep in mind, you can write this wherever you want on your paper. I don't have a lot of room over here, but this is very true. So let's go ahead and confront this long division problem right here, and I'll take you through the process. But when we set this up very much the same way that we set up a division problem by putting our divisor on the outside and our dividend on the inside. So I'm going to start with this 2x to the fourth plus 4x to the third minus 5x squared plus 3x minus 2, and we are dividing this by this divisor, the second degree divisor, x squared plus 2x minus 3. So we've got this fourth degree polynomial divided by the second degree divisor. So what we're going to do is the same thing we worked with over here, except for we're going to work left or right and look at only the terms in front of these two expressions. So when I say work left to right, we had started with the 1 here and then worked our way across the 2 and then the 8. We're always going to look at this very first term here, this 2x to the fourth. And what I'm going to ask is, how many times does this outside polynomial go into this right here? Essentially, though, we're only going to pay attention to this first term of the divisor. So recall that when I say, well, how many times did 2 go into 12, I was really asking, what could I take times 2 to get 12? By asking this question, how many times does x squared go into 2x to the fourth? I could really answer this the same way by asking, what could I take times x squared to get 2x to the fourth? Now the answer to that question simply is I could take x squared times 2x to the second, and that would give me 2x to the fourth. So what I'm going to do is I'm going to put that 2x squared up here, and you'll notice that I stacked it on top of my x squared term. And that's just because the place value here is important. So once we've divide. We're going to write down our steps here. 1, divide. You know what, I'm going to write it over here. Give ourselves some room. 1, divide. The next step in this process is always going to be multiply. And what we mean is we're going to multiply this value that we put up top times all of this number out front, which is this entire polynomial expression. So look what we get here. We say 2x to the second times x squared. You ought to get 2x to the fourth, but see, you created that. You made that happen. That was the question we were trying to answer. Now the rest of this is just collateral damage. We say 2x squared plus 2x would be 2 times 2 is 4. And we say x squared times x is x to the third. We say 2x squared times a negative 3, now I get negative 6x squared. So our next step in this process is going to be the subtraction. Just like we do with regular long division here, we are going to subtract off all of this value. So I want to make clear that you should put parentheses around this entire thing, because when we put this minus out front, really what we'll do is we'll go back and switch this to positive and then switch everybody's signs in here. So this would become a minus, this would become a positive here. And then what we'll do is we'll just add these expressions. So I get the 2x to the fourth and negative 2x to the fourth to cancel. As a matter of fact, in this instance, we get our 4x cubed and negative 4x cubed to cancel. And if I said, well, how many x squareds do we have? I know I have x squareds. Well, positive 6 and negative 5 would give you one of those things. So to continue our division here, what we'll do is we'll carry down the next term, this plus 3x. And then we'll just begin again, except for this time, just like last time we said, how many times does 2 go into 1 and carry this out? Then we asked how many times does 2 go into 12. Well, now I'm going to ask how many times does this leading term x squared go into this leading term here? Or in other words, what could I take times x squared to get this x squared? And the question, we asked there has an answer of 1. I could take 1 times x squared to get x squared. So that positive 1, notice that I'm going to put it above my constants here. I want to keep my place values straight. So I would say 1 times x squared is x squared. 1 times 2x is 2x. And I have 1 times negative 3 is negative 3. So we're going to put parentheses around this and subtract the whole thing. And you'll notice that I have nothing to subtract this negative 3 from. So we can go ahead and carry down this last constant 2. So distributing this negative through, we're going to say now this becomes a subtraction, this becomes addition. I would say that 1x squared and negative 1x squared, they cancel. And I have 3x's minus 2x's give me an x. And negative 2 constants plus positive 3 constants is x plus 1 here. So I would say that now this x plus 1, what we want to do is give this a name, and this would be our remainder. And previously in this division algorithm, we called this the r of x expression. Okay. So what we'll do with our remainder is simply this. We say we've got our divisor and dividend. This thing right here really is our quotient. And then we'll say plus the remainder now on the outside. The thing is, when you write the remainder, we say x plus 1 was left over. Just like here we had nothing left over, right here. But we say over the thing I was dividing by, which in this case is x squared plus 2x minus 3. I'll put a big box around this right here. So So what I want everybody to see is that using the division algorithm, we could basically say that we could rewrite the original polynomial, which was this 2x to the fourth plus 4x to the third minus 5x squared plus 3x minus 2. I'm going to write equals. I'm going to carry this down here. But we could say it's equal to the thing we were dividing by, x squared plus 2x minus 3, times the answer that we got, which was 2x squared plus 1. And then we would say plus the remainder here on the outside, which in this case, the remainder is, in this case, x plus 1, all over the thing that we divided by, which was this x squared plus 2x minus 3. We would get that there. So you can see that we get this expression right here, and it means the same thing as what we started with. So the last thing I want to leave off with before we leave this video is, so now that we've divided this, was this a factor of the original polynomial? And what we know about factors is it can't be a factor unless this remainder was equal to 0. In other words, it had to go in evenly. Just like I know 2 is a factor of 128, I could look at this and say, because we did not leave a remainder of 0, then this thing that we divided by is not a factor of the original polynomial. Cheers.